Welcome to Science Lab. The signs are happening because Jesus is coming. Every day, we are looking at some of the signs that are happening around us. In this episode, we are going to see about the strange things that are happening in the sky.
Over the last 100 years, advancements in science and technology have allowed us to learn so much about where we came from and how our planet has developed over time. With our discoveries of old fossils, we know that life on Earth has existed for thousands of years. But with the Earth itself believed to have formed about thousands of years ago, we still have very limited knowledge on what caused life to form in the first place, and much of the evidences on how it may have developed has actually been destroyed by the very life that it created.
Sadly, we don't have a time machine, but we can look for places in our solar system that emulate early Earth. That's where Saturn's largest moon, Titan, comes into the picture. Although it's about half the size of the Earth, Titan has the characteristics that we think are very similar to Earth in its early days. Titan has a thick atmosphere at around 4.4 times denser than Earth's, and is the only moon in the solar system to have any noticeable atmosphere at all.
Titan also has large pools of liquid which follow a similar cycle to the rivers and seas we have here on Earth. But instead of water, Titan has seas of methane which evaporate into clouds, causing it to rain liquid methane. In terms of scientific information, Titan is a gold mine for scientists. But sadly, it's extremely difficult to get to, and because it's entirely covered in clouds of methane, it's nearly impossible to study the surface from a distance.
In 1997, a collaboration between NASA, the European Space Agency, and the Italian Space Agency launched the Cassini space probe on a 7-year journey to reach Saturn. The probe was designed to study the entire Saturn system, including its rings and natural satellites. But Cassini didn't make the 7-year journey on its own. Attached to the space probe was a small lander called Huygens, which was hoping to become the first spacecraft to land on Titan. Several months after entering Saturn's orbit, Huygens separated from Cassini and started its journey towards Titan, and began sending back vital details about Titan's environment, like the fluid properties of the atmosphere and the nature of the moon's surface. As it descended, Huygens recorded accelerometer data, which could be used to deduce properties like density of the fluid, as we knew the aerodynamic properties of the probe. It took temperature and pressure readings to teach us about the thermodynamic properties of the atmosphere. After 2.5 hours of descending through the unknown, Huygens successfully landed on the surface, making it the furthest spacecraft landing from Earth ever completed. Although it was only designed to survive for about 90 minutes while on the surface, Huygens successfully recorded and sent back 350 images, revealing a world eerily similar to ours, with sharp hills and valleys and rivers of methane cutting their way through the landscape. As our quest to learn more about the origins of life continues, NASA's new mission called Dragonfly will begin its journey to Titan in 2026, and the work of the Cassini and the Huygens mission will be vital to its success.
Dragonfly is a mobile lander fitted with 8 large rotors that will help it fly around the surface like a drone. An incredible difficult engineering challenge, and the data gained from the Huygens will be insanely valuable when designing the drone. Everything from its sensor layer, battery capacity, energy source, and propeller's design will be dictated by what we learn. And those are exactly the engineering challenges we are going to investigate today.
Dragonfly will have many of the same scientific instruments as the Curiosity rover. It will have skid-mounted drill to take soil samples and run it through a mass spectrometer to learn more about the soil composition. It will be capable of quickly analyzing elemental compositions at landing sites before landing, using a neutron-activated gamma-ray spectrometer.
This instrument typically needs cryocooling, but thanks to Titan's sub-zero temperatures, this instrument can be passively cooled. It will, however, need to generate its own neutrons rather relying on cosmic rays to generate them, as the atmosphere blocks too much sunlight. When it lands, a seismometer will give us information about quakes and reveal the thickness and nature of Titan's icy crust, sitting above what is thought to be liquid water ocean. We think this because Cassini witnessed the surface shifting in position by 30 kilometers in just 2 years, indicating that the crust is floating on top of some kind of liquid layer. We can also look forward to incredible photos of Titan's surface, just like the photos we are currently getting from Mars. Since the air is thicker on Titan and the gravity is 1/7 of Earth's, Dragonfly will be able to achieve more thrust on a planet that needs less lift, drastically reducing energy consumption compared to Earth. Yet finding that energy to fly on the surface of Titan is not easy. Due to Titan's distance from the Sun and its thick atmosphere, the sunlight on Titan's surface is around 100 times weaker than it is on Earth, making solar panels impractical. Thankfully, we have a lot of practice in a different type of energy source through missions like the Curiosity rover, which was powered by radioisotope thermoelectric generator. RTG's work is converting the heat from the natural decay of a radioisotope into electricity. Now, this isn't traditional nuclear energy. The RTG does use radioactive materials to generate electricity, but not through nuclear fission. It uses a simple principle called the Seebeck effect to generate electricity. The Seebeck effect essentially allows us to generate an electric current through a heat differential, as charge carriers will move from hot to cold. So if we have a heat source and a way of cooling, we can generate a sustained electric current. Thankfully, radioactive substances generate heat as they decay. Choosing a suitable radioactive material is our first challenge. With many spacecraft, a lightweight compact design is a paramount, but we also need the material to have a long half-life to ensure a long-lived energy source. We also need it to primarily produce alpha waves, as this form of radiation is most easily converted to heat in a compact space. As a result of these requirements, plutonium-238, strontium-90 and curium-244 are the most commonly used fuels. Next, we need a material which is both a thermal insulator to maximize our temperature differential and an electric conductor to maximize our current. These two material properties are typically linked. Materials like copper are both a good thermal and electric conductor, and a material like iron is a poor thermal and electrical conductor.
And now, it's the time for the trivial question of the day. How many moons does Saturn have?
And the options are option A 1, option B 12, option C 62.
Let's see the answer after a short break. Welcome back to Science Lab. The science are happening because Jesus is coming. Before the break, I asked you the trivial question of the day. How many moons does Saturn have?
Option A 1, option B 12, option C 62.
And the correct answer is option C, 62.
Saturn has 62 confirmed moons, of which 9 are waiting to be officially named. Saturn's largest moon, Titan, is bigger than both Mercury and Pluto. Titan has a very thick atmosphere, which is mostly nitrogen. Earth's atmosphere is also mostly nitrogen. Saturn also has many icy moons like Mimas, which has a large crater that is 1/4 of the diameter of the moon, and Enceladus, which has very dark material covering one side and very bright material on the other side. Some of Saturn's smaller moons help keep Saturn's rings stable by orbiting in or near the rings. These moons are called shepherd moons and use their gravity to help the small ring particles in a stable orbit. Some of the gaps in Saturn's rings are caused by these moons.
Using these materials in the conjunction can create a crude thermoelectric generator, but the efficiency is very low. If we can create a material with the best of both properties, then we can achieve a higher efficiency, leading to the use of materials like lead telluride and tags, which is an alloy of tellurium, silver, germanium, and antimony.
The thermal electric generator used for the Curiosity rover could generate 110 watts of electrical power. But we will lose some power generation capability during Dragonfly's 8-year journey to Titan, as we cannot turn a radioactive element on and off on demand to conserve energy. In fact, Dragonfly's cruise vehicle will need to be equipped with radiators to breathe that heat energy into space to prevent overheating, just as the Curiosity rover did.
We will also lose energy to keeping the craft at operating temperature, as the surface of Titan can reach temperatures as low as minus 180 degrees Celsius, and to keep some vital systems and scientific experiments running, leaving us with about 75 watts to charge while on the ground in a best case scenario. All of our activities will occur during Titan's daylight hours, so we will be aiming to charge our batteries during Titan's nights, which lasts 192 hours, the same as their daylight hours. So it makes sense to make a battery charge fully in those 192 hours, giving us a 14 kilowatt hour battery. For comparison, a typical Tesla battery is about 75 kilowatt hours, with a specific energy of 100 watt hour per kilogram that will make our battery 140 kilograms. In practice, a smaller battery will probably be used, and even a 30 kilogram 3 kilowatt hour battery would provide up to 2 hours of flight time at 10 milliseconds, providing a massive 72 kilometer range. Even more incredible when you consider the Curiosity rover has only driven 21 kilometers over the past 7 years of its time on Mars. Of course, Dragonfly won't fly its maximum range in one hop and will likely take shorter, safer hops between interesting points during Titan's day, and one of the most impressive things about this mission is how the spacecraft will navigate its way around the surface. Since Titan is so far from Earth, just sending basic information to Earth and from Earth will be difficult. The energy requirements to transmit data rises dramatically as a result of the inverse square law. The Huygens probe had the advantage of being able to relay information to the Cassini space probe, which had a larger antenna and a higher power. Unfortunately for the Dragonfly mission, Cassini is no longer in orbit around Saturn, falling into Saturn's atmosphere in 2017. So Dragonfly will need to dedicate both precious power and weight to a large high-gain antenna in order to communicate with Earth's deep space network. On top of the additional energy and weight requirements, Titan B-Roll E3, the average round-trip communication time is around 2.5 hours, making it impossible to fly the spacecraft in real time. Instead, Dragonfly will fly using its own vision, much like the self-flying drones we have here on Earth. Dragonfly will use its cameras along with the onboard gyroscopes and accelerometers to travel from one point to another. Dragonfly will be trained to identify suitable landing sites that are flat and free from any obstacles like large rocks and rough terrain.
Originally, Dragonfly was intended to fly with a single rotor, but since helicopters are mechanically complex in the way they vary the rotor's pitch to vary lift, the idea was never developed. But with the surge in multi-rotor done technology over the last decade, the idea for a quadcopter became much more feasible. Dragonfly will feature a total of 8 rotors mounted in pairs in a quadcopter layout.
Unlike a helicopter rotor, which is designed to spin at a constant rate, the speed of each rotor can be throttled electrically to vary the amount of lift generated. Although it's less efficient to have rotors in this over-under configuration compared to a regular quadcopter, it does provide additional lift while giving some redundancy, as the aircraft will be able to achieve stable flight even with the loss of one motor or rotor.
Since Titan's atmosphere is made up of mostly nitrogen and is much colder than Earth's atmosphere, the viscosity is also much lower. Along with the higher density, this means that the rotors on Dragonfly will be operating in a fluid with a much higher Reynolds number than they would if they were operating on Earth. Reynolds number is essentially a quantity that informs engineers whether laminar or turbulent flow will develop. It's a little confusing as the number is not constant for every situation and depends largely on the application. But in general, it can be described by this equation for flow in a pipe, where inertial forces trying to keep the fluid flowing are the numerators, and viscous forces trying to slow down the liquid are the denominator. Here a higher density will increase Reynolds number and thus the increased likelihood of turbulent flow, and a lower viscosity will also increase it. Exactly the scenario we are encountering on Titan. As a result, the propellers had to be designed differently to work as efficiently as possible on Titan. They are in fact much closer in design to wind turbine blades than normal propellers with a large amount of twist in the aerofoil. These propellers are a meter in diameter, much smaller than any wind turbine blade here on Earth. But as a result of that higher Reynolds number, the same design principles are applicable. Wind turbines are also designed to be resistant to a buildup of surface dirt, which will be a valuable property on another planet with maintenance crews billions of kilometers away. We also need to factor in the lower speed of sound on Titan, which is about 194 millisecond versus 340 millisecond. So shock wave formation can occur much sooner at the tips of our propellers. This means we have to be mindful of tip speeds, which are determined by prop diameter and rotational speed. Even with these unique environmental factors, Dragonfly will have a mass of around 40 kg with fantastic range and max speed.
Allowing Dragonfly to first land in the sand dunes of Titan's equatorial region before eventually making its way to Selk crater, an impact crater thought to contain all the building blocks of the life that we are familiar with here on Earth, and may just give us some clues about humans' ultimate question: how did we get here?
Bible says in Obadiah chapter 1 verse 4, "Though you ascend as high as the eagle, though you set your nest among the stars, from there I will bring you down, says the Lord."
What is foretold in the Bible is happening again in our lifetime. All this shows that we are living in the last days. Lord Jesus Christ is coming again very soon. Thank you for watching this episode. Don't forget to tune into the Science Lab next time.
Send us photos, videos, news and YouTube links which are worth sharing. And also you can send your feedbacks to our email address sciencelab@angeltv.org. Suppose if you have missed any of the episodes, don't worry, you can watch it again and again in our Science Lab YouTube page. But don't forget to like, share and comment on the video.
Ask your friends and relatives to watch the Science Lab so that they will know that we are living in the last days. Remember, signs are happening because Lord Jesus is coming.
Maranatha.